Today's lesson, I want to talk about one of my favorite topics, which is the ocean. As I've been mentioning, I am from New Jersey, and so I literally grew up within about a mile of the ocean. Um, Pretty much it has been a part of my life the entire 40 some odd years that I've been on this planet, and it still amazes me the power of the ocean and the fact that it essentially has become something that we really need to pay attention to as we go forward in terms of climate change, sea level rise, and then also planning about um, where do humans, in terms of their what seems to be addiction to live at the coastline, are going to be in the next, short term couple of years, and then also long term, 50 to 100 years from now. So, everybody loves to have this idea of like this beautiful house by the ocean, right? And you can see in the background here, there's this beautiful, right? Looks like this little place right there. 50% of the US population lives within 50 miles of a coastline. Now that doesn't really maybe surprise you all that much. That there is sparser population, for example, in the Midwest and in the Southwest, but of course along coastlines, we do have quite a bit of larger U.S. population. And it's not just the U.S., and it's not just within 50 miles of the coastline. If we break it down even more, currently, over 200 million people live along coastlines that are less than 5 meters above sea level. And that's really important because as climate changes and sea level continues to rise, it's those populations that are going to be closest to the coastlines that are going to be the most vulnerable to sea level increase. So right now, about 200 million people live along the coastlines at about 5 meters above sea level. But by the end of the 21st century, that's going to double or then some, maybe even more. So that's a huge amount of global population living in areas where there is just a couple meters of buffer zone between current sea level and what is projected to be the sea level rise. In Europe, 13 million people would be affected by just an increase of sea level of 1 meter. That's, 3 feet or so. And at the rate that sea level is rising, people are projecting that could happen, within just a lifetime or so. So let's look a little bit more about kind of, what's going on the coastlines, what are the coastline landforms, and of course, then what do we do about it when we have to deal with the human interaction with coastal processes. If we look at areas that are most at risk, I know this looks like a map with tons and tons of green on it, right? And so the green means that you're not very much at risk for sea level change affecting you unless sea level gets up into these ranges right here. And remember, these are rates of increase that are showing, meters above current sea level. So this is, 20 meters above sea level currently, or up to 80. If you look at this map closely, you will see that there are lots of coastlines, however, that would be affected just by 1 to 2 meters of sea level rise. And in fact, there are large portions of entire countries, especially over here, that would be significantly affected by that. While you may think that, places that are in the green are relatively safe, I will also just put on your radar screen that if all ice on land right now melted, so for example, that is Greenland, Iceland, Antarctica, if all ice on land melted, you would see a sea level rise of about 70 plus meters. So all the areas that are in green may not be totally safe, essentially, because we could see, if we melted all land ice, up to 70 plus meters of sea level rise. Of course, that's if we melt everything, but still, that is something to kind of keep in mind. So what's going to affect essentially coastal landscapes? Like what is going to be the main factors that tell you whether a coastline will be inundated, might have damage associated with sea level change and all that sort of stuff. So we're going to go through each of these variables here, and we'll talk about how the coastal landscape, right, the way that the coastline actually looks is going to be variable and will depend on a bunch of different things. And the first thing I want to talk about is the stability of the coastal region. And what I mean by stability, right, is its tectonic stability. So what I'm talking about in terms of stability here, tectonics, is are we on an active margin or are we on a passive margin? And remember what those two terms mean. An active margin is where a coastline, right, the edge of a continent, coincides with the edge of a plate boundary. So a good example of an active margin coastline would be, right, California. A passive margin is where you have instead a coastline that does not coincide with a plate boundary. So a good example of this would be North Carolina. Our nearest plate boundary is way out in the middle of the Atlantic Ocean, so we don't sit on a plate boundary, and we are therefore considered a passive coastline or a passive margin. California, right, is on a transform boundary right there, right, where plates are literally kind of sliding past each other this way. And North Carolina is a passive margin. We're not sitting on a plate boundary, but our nearest plate boundary is in the middle of the Atlantic, and it is a divergent plate boundary. That would be the mid-ocean ridge. So we'll come back to the slide in a couple of minutes when we talk about the types of materials, waves, tides, and then long-term changes in sea level. But let's start by looking at the differences in coastlines on active and passive margins first. If we look at kind of the major topographic features of the seafloor, and I'm not talking about topography of the continents, right? I'm talking about what's the topography on the seafloor. You'll remember that, where there are plate boundaries, so for example, I'm drawing the mid-Atlantic ridge right now, right? This is the divergent boundary that's at the mid-ocean ridge closest to us. And then there's another big spreading ridge over here. And then there's the transform boundary here, huge subduction zone, right, around the Pacific. So places where you see trenches, right, trenches, those are very deep parts of the ocean. Places where you see the terms ridge or rise, these are places where usually you have spreading centers, right, where you actually have now new seafloor being created. So these are the high points in the seafloor. And then between those areas where it looks relatively flat, right, this is the abyss. This is the really deep flat parts of the ocean. Another big deep trench right here off of New Zealand. So we see trenches, really deep parts. We see ridges and rises, so places that are relatively high. But you'll notice too that, right, like there seems to be this deep sea trench pretty much along the left western side of both the North and South American land masses. And then over here on the eastern side of North America and South America, these are both passive margins here. So is this side. But their western margins, these are very much active, right, all the way up here. So are there different features associated with active and passive margins? You bet. So we're going to look at the difference between what features you get on passive margins versus what coastal features you get on active margins. So first I want to look at what's going on passive margins. And so here's a kind of a seafloor picture, but I'm focusing on what's going on the eastern margin of North and South America. So this is the passive margin side. As you go from the continent into the ocean on a passive margin, usually what you will meet is in this order, right? On the continental margin, you will first hit the continental shelf, then the continental slope, and lastly, the continental rise. These are all very, very close to the continent itself. As you then get further away from the continent, you will hit the Abyssal Plain. And finally, way out here, right in the middle of the ocean, you're going to finally hit the mid-ocean ridge. So let's look at the features of each of these continental margin and abyssal plain morphologies, these landforms. We'll start with the continental shelf, the slope, and the rise. If we took a cross section, so literally if you kind of walked, if you could, from North America straight out into the ocean, across the Atlantic, and then back up to Spain over here, and you essentially mapped out what was going on the seafloor, this is what you would notice. Now remember, this is not to scale, but if you started over here, right, here would be point A, what you would notice is that as you walked off the continent and started to get into the ocean, first off, the seafloor would very gently just kind of start to get deeper and deeper and deeper. you get into the first thing called the continental shelf. That's actually this light blue thing here. All this from the actual beach and this kind of shallow region out here, all the stuff that I'm coloring in red, okay, that is the continental shelf. It's relatively shallow, and here's the cool part. It's actually still part of continental crust. So at some time in Earth history, when sea level was quite a bit lower, this actually was just part of the North American continent. In fact, there's dinosaur bones out there, there's dinosaur footprints and everything else. And the only reason it's underwater right now is because sea level has increased. So we first hit the continental shelf, and that's a passive margin. Remember, this is a passive margin feature. And then as you keep walking into the ocean, you'll notice that the continental shelf drops down pretty sharply. This is where you hit the continental slope. The continental slope here is drawn as like this precipitous drop off. It's not. It is steeper, of course, than the continental shelf, but remember, this is drawn with huge exaggeration so that you can actually see all the features. The Continental Rise will be right at the bottom here of the continental slope. I'll explain that in a minute. But then this kind of really flat region out here, this is called the Abyssal Plain. The Abyssal Plain was at once thought of as essentially the deepest, flattest, boringest part of the ocean. But we now know that actually on the Abyssal Plain, there are these little, volcanoes, right, or little things that don't, little ridges that don't reach the sea level, right, which would be up here. And so we call those things seamounts, right? These are little volcanoes that don't reach the top of the ocean. And eventually, if you keep going out into the middle of the ocean, what you will hit is the mid-ocean ridge, right? So this is the divergent plate boundary that is closest to us. It's the mid-ocean ridge that lives right here. Okay, so let's look now, and you'll notice, by the way, that it's a mirror image on the other side. If you go over here to Spain, look, there's a little continental shelf, a slope, a rise, then you get to the Abyssal Plain, couple of seamounts here, and then you eventually get back to the mid-ocean ridge. So the continental shelf, and I'm just going to show you another picture here of kind of the mid-Atlantic states. This is the continental shelf, this kind of light blue area right all in here. It is very wide, at least on passive margins, right? It is very wide, and it's relatively flat. So you'll notice that we're kind of showing the continental shelf in cross-section over here. It extends from the shoreline to the beginning of this drop-off here, which is the continental slope. The cool thing about this is that it's relatively shallow, right? It's less than about 200 meters deep. And you'll notice that its distance, right? Its distance from the coastline kind of varies a little bit depending. It's actually really small in terms of its width right here off Virginia, but then off of like Florida and Georgia, it's actually quite a bit larger. So it may extend, hundreds of kilometers offshore. Now remember, a nice big broad continental shelf is a feature of passive margins. Remember, we're talking about passive margin features right now. You do not get a broad continental shelf on active margins, mainly because the active tectonics, right, either the grinding of plates next to each other or the subduction of a plate, usually tends to grind up the continental shelf. So continental shelves, especially broad, kind of flat ones like this, are usually found on passive margins. As we go a little bit deeper, this is now, we've kind of left, this is the continental shelf right here. We're now going to kind of talk about, as you go further into the ocean, we hit what's called the continental slope. This is the transition between continental crust and ocean crust, kind of right in here, right? The continental shelf is, as the name suggests, part of continental crust. But as we start to now slope down towards the abyssal plain, we're now going to kind of segue and leave continental crust and become more ocean crust. As these are drawn, right, they're almost always drawn as these huge steep drop-offs, but notice they're only about 4 degrees. The angle of the slope is only about 4 degrees. So we're drawing them very steeply, but this is where you're now going to drop into deeper ocean water. It is a mud-draped slope that is now marking the end of the continental shelf, right, the oceanward end, and we're now going to drop down into the deeper parts of the ocean. You might notice especially on this image right here. See all these kind of deep, dark kind of canyons carved into this. A lot of the continental slope does have these deep submarine canyons. Many of those are formed by underwater landslides or slumps. And so we often call these turbidity flows. Turbid just means like all mixed up and chaotic and whatever else. So as you kind of release these landslides from up here, they come careening down the continental slope, and they usually leave kind of a landslide scar that are then becoming these submarine canyons. Here's another example of what some of these submarine canyons look like, right? You see these steep wall, these V-shaped, steep-sided canyons right here. That's where material used to be here, and it's now slid down the continental slope. Now, if we're going to constantly be landsliding stuff off the continental slope, where do you think it's going to collect? It's going to collect right here at the bottom of the continental slope, and we call that the Continental Rise. So the Continental Rise, the rise part, is suggesting that you kind of get this little lump of sediment right at the base of the continental slope, and the rise is due to the fact that there's all this landsliding material coming down, and it's just going to kind of all pile up right here at the Continental Rise. So the Continental Rise is relatively, small. It's a narrow, feature in the ocean, but it's a gently sloping apron of sediment. So, right, pile up or whatever else. So the sand and the mud that is now kind of sliding off the continental slope, and it kind of just collects at the bottom here like this little lump. It would look very similar, right? If you could actually see it, it would look very similar maybe to an alluvial fan or a delta, but it would just be underwater. So they may include, instead of deltas or alluvial fans, they may include submarine fans. So as these landslides kind of come down here, they make this fan shape or delta shaped accumulation of sediments like this. Those are the submarine fans there that can collect several kilometers of sediment. So they can actually become pretty thick over time if you have a place that is constantly landsliding into the same part of the continental rise. All right, so now we've gone from the continental margin, right? The continental margin was the shelf, the slope, and the rise. Now we're going to leave the continental margin and we're going to go seaward even more, and we're going to get into the abyssal plain. Remember how I told you also, look, here's continental crust and here's ocean crust. The transition between the two is kind of right after you get to the continental slope and the continental rise. Let's look at the abyssal plain now. 4 to 6 kilometers below sea level. So this is usually very, very deep. 4 to 6 kilometers below sea level. It's considered to be one of the flattest surfaces on the planet. But that doesn't mean that everywhere on the abyssal plain is extremely flat, because we often do get these little submerged volcanoes out here that we call seamounts. Okay, we call them seamounts when they don't reach the surface of the ocean. If they reach the surface of the ocean, right, and they're little volcanoes, we usually call them volcanic islands. And so Hawaii is a good example of an actual volcanic island. But when they don't reach the surface and they're all still underwater, we would call them seamounts. While the continental shelf, the slope, and the rise are usually pretty sandy, sometimes they have mud in them, when you get into the abyssal plain, there's really extremely low energy out here, right? There's no currents, there's no waves, you're 6 kilometers deep, there's not even any sunlight down there. So there is extremely low energy happening at the abyssal plain. And so there's nothing really to mix up sediment. So sedimentation rates are extremely slow. Okay, the buildup of all this sediment in the deepest parts of the ocean is on the order of a millimeter per 1,000 years. A millimeter, I mean, that is pretty darn tiny. Okay, that's 1/10 of a centimeter per 1,000 years. So it takes 1,000 years to deposit just this little tiny bit of sediment. because there's really no energy to bring sediment down to the bottom of the ocean. The stuff that does get out there is really fine-grained stuff. Okay, so you're not going to see, boulders or cobbles or anything like that out in the abyssal plain. You're just going to see really fine-grained clay-sized materials, maybe some wind-blown dust that got out there and then slowly settled through the water column. And the other thing that you might notice in abyssal plain sediments are just the kind of dead shells of little tiny microorganisms, things like maybe plankton or diatoms. And these things settle out of the water column extremely slowly. Okay, so that's what's giving us our sedimentation rate of, a millimeter per 1,000 years. So generally speaking, as you get deeper and deeper into the ocean from the shelf out towards the abyssal plain, what you're going to notice is that grain size gets smaller, right? The shelf stuff is where you're going to get wave action and you're going to have sand. The abyssal plain is where you're going to get only fine-grained particles because of the very low energy that's happening way out in the deeper parts of the ocean. The other cool thing that's happening, though, on the abyssal plain is that when you get to some of these seamounts, or even when potentially you get to the mid-ocean ridges, there is a lot of volcanic activity happening at these ridges. And so we do get these what are called hydrothermal vents. And you guys might have seen these on like the Discovery Channel or whatever. They're called oftentimes black smokers. And so this is one of those vents right here. And this is supercharged, superheated water and ions coming out of one of these hydrothermal vents. Tons of minerals in this, all sorts of stuff like sulfides, tons of nutrients also. So black smokers actually are a result of magma being very close to the surface, right? Just underneath it right here. And this could be a hydrothermal vent. This could even be a mid-ocean ridge, right? Where you've got a spreading center. And so the magma underneath it is the heat source. And then as seawater kind of circulates into the hydrothermal vent or into the mid-ocean ridge, that seawater then gets charged with like iron sulfides and calcium sulfates and things like that, which are super important nutrients for a lot of the crazy critters that live around some of these hydrothermal vents, like these like 6-foot tube worms, these blind crabs and all sorts of cool stuff. So check out this video if you want to see some of the cool critters that live around these hydrothermal vents. It's pretty neat stuff. So all of the features that we just discussed, right? The continental shelf, the continental slope, the continental rise, and then the abyssal plain, those are all features of passive margins. Now, if we look at an active margin, here we're now going to use the west side of South America, right, as a good example of an active margin. And then we're going to go this way into the Pacific. We're going to cross the East Pacific Rise, which is actually a mid-ocean ridge. We're then going to hit the Tonga Trench, right, which is a subduction zone. And then we're going to hit the Australian Plate. And this is now a passive margin over here, even though we're active here, and active here. So if we start at South America, what you're going to notice is that as you move off the continent into the ocean, you don't have a shelf, a slope, or a rise. You drop immediately into the Peru-Chile Trench. The reason for that is because this plate, the Pacific Plate, is moving to the right, and it is subducting underneath South America. So you can imagine, right, like this plate's actually diving down like this underneath South America. So that creates a trench. So we have a trench now instead of our passive margin features, right? No shelf, no slope, no rise, because instead we're having active subduction right here. We're crunching up all of our passive margin features, and instead we're seeing a deep sea trench because of the subduction zone. As we go further out into the ocean over here, right, we hit the East Pacific Rise. Remember, the East Pacific Rise is actually a spreading center, so that's what's pushing this Nazca Plate here towards the South American Plate, but it's also pushing the Pacific Plate here towards the Australian plate. Remember we said older, colder, denser, deeper. So we're now seeing the subduction in the Tonga Trench as this guy moves to the left and the Australian plate moves to the right. The Pacific plate here now actually dives down underneath the Australian plate this way. And so now you've got another trench, the Tonga Trench over here, another active margin. But the Australian plate, right, the Australian continent, the edge rather over here, this is passive, right? Its closest plate boundary is over here at the Tonga Trench. So what you'll notice is that they do have a continental shelf in Australia because right now they do have a passive margin. Its nearest plate boundary is way over here in the Tonga Trench. So you would get a continental shelf slope and rise off the east coast of Australia, but you wouldn't see it off the west coast of South America because that is an active margin. So that's how the stability of the coastline, and again, we mean tectonic stability of the coastline, affects the underwater landforms that we see. Let's look at now how the nature of the rocks or the sediments at the shoreline can cause the coasts to look very different. So I'm going to show you some pictures from around the US to kind of tell you why beaches look kind of different depending on where you are, especially around the US. So close to home, we'll start here. Here's a sandy kind of coastline of North Carolina. This would be the open ocean here, right? This would be Pamlico Sound behind it. And these here, right, these are the barrier islands. So we here have at the coastline of North Carolina, we have barrier islands, which essentially are just really big dunes that are actually sitting offshore, and they keep the ocean separated from the sound behind it. Outer banks or the barrier islands like this are very, very important to helping to protect the mainland. So the mainland of North Carolina would be way back here, right? They protect the mainland from things like hurricanes and flooding because they kind of act as a buffer zone, right? So the hurricanes come and they kind of bash the outer banks, but the outer banks then kind of absorb a lot of the intense storm activity, and it keeps it from hitting, you know, the mainland of North Carolina. But, you know, where we have sandy beaches like this, oftentimes, not always, but often you will get barrier islands and have a coastline that looks similar to North Carolina. So New Jersey has barrier islands, so does Maryland. Texas and the Gulf Coast has several barrier islands. So on passive margins, we sometimes get these sandy barrier coastlines. Other places where we have passive margins, for example, you're looking south along the mainland of Maine, because we don't have, because we have a lot of very, very strong, very resistant, this is granite, you can't see it if I write it in red. How about this? We do granite, yeah, granite bedrock. The granite bedrock that we have up in Maine and a lot of the New England states means that since this stuff is really resistant, right, this is really hard to break down, we don't get sandy beaches, right, in New England. Instead, we get rocky beaches. And this rock, since we can't break it down, remains hard, gives us kind of steep cliffs or kind of rocky coastlines like this. And it has been modified, but it's only been modified when we had huge glaciers rolling over it. We haven't made a ton of sediment. There's not a ton of big rivers, right, breaking this stuff down and making sand like it does in North Carolina. So here we've got really strong bedrock, which means that now we've kind of got a very resistant, very rocky coastline. This is the southern coast of Australia. And here we also have bedrock right at the coastline. But the bedrock here is not made of granite. The bedrock here is made of sandstone. And so the sandstone that's being shown right here in all these cliffs is a little bit softer than granite. So what happens is that as the waves constantly crash into the coastline here in Australia, they are able to slowly wear away the sandstone cliffs, leaving these beautiful things. This is actually called the 12 Apostles. that stand off of the southern coast of Australia, but these are called sea stacks. So these are pieces of what used to be, right, the coastline. This actually was the coastline, and the waves have actually kind of cut around these so that now they're just kind of standing alone as these stacks of rock. And as you know, more and more of the Australian coastline erodes, you'll probably see more and more sea stacks being formed as these eventually crumble and fall down. The reason why this coastline has this look, of course, is because it does have a rocky coastline, but the rock is not as resistant as granite. The sandstone is easier to break apart by the waves, and so you get these cool looking sea stacks. One of my favorite, right, are coral reefs and places where you get a lot of carbonates. So here is the coastline of Florida. So here would be your land over here, and you've got very shallow water here. You can see that the color of the water is different. And then all these places, you can actually see all this kind of pretty stuff underneath that looks like rock and whatever. These are reefs. So shallow, warm, tropical regions where there are abundant warm waters and mixing and lots of sunlight. A lot of times what you'll get is coral buildup. And so you can make these beautiful coral reefs. And again, you need the right conditions to make corals. You need the nice warm waters, you need sunlight. So they usually only form within about 30 degrees north and 30 degrees south of the equator. So we don't usually get, coral reefs up in, Maine, but usually these are kind of warm water features that are found in shallow waters like Florida, the Bahamas, and the Caribbean. So that's how the nature of the rocks and the sediments can make the shorelines look a little bit different. Let's kind of work now into talking about waves and tides, because the wave energy is actually going to be super important, because the wave energy is going to then affect how you break down the rocks or the sediments at the shoreline, but also too, it will have an effect, for example, on how do we generate storm waves and how do storms really affect the shape and look of the coastline. So first of all, if we talk about kind of, waves and currents and things moving water around the world's oceans, we have to remember that there are lots of different things going on in the world's oceans. There are waves that happen right at the ocean's surface. So wave action is going to be kind of just a superficial feature of the world's oceans. But while the waves are moving, deeper into the ocean, you also have tons of different currents, and the currents are helping to move water, and that water is different temperatures and different salt contents, and it mixes the world's oceans thanks to all of these currents. So if you look at, you are here, I don't know if you can see that, but you are here, right, on the east coast of North America. I think one of the currents that you guys are most familiar with, right, is here. This is the Gulf Stream. The Gulf Stream is part of the North Atlantic gyre, and a gyre just means, right, like a circular motion like this. And so you already know that thanks to the Coriolis effect, things that are, wind and water currents in the northern hemisphere tend to move clockwise, and that currents, wind and water in the southern hemisphere tend to move counterclockwise. So notice that we have a North Atlantic gyre and we have a South Atlantic gyre. Gyres are just fancy names for some of these currents that kind of move in a circular fashion. So so now you've got the Gulf Stream. If you watched Finding Nemo, right, here's the EAC, man, right? There's the East Australian current. This is a cool current right here. This is the Benguela current, which actually takes super cold water off Antarctica and brings it up the western coast of southern Africa, making the Namib Desert right here an extremely dry, but weirdly enough, an extremely cold desert. It's pretty neat. So anyway, these currents are moving water, they're moving heat and stuff throughout the world's oceans. That's moving the oceans and mixing them, but on a more local scale, right, at the surface, we're also mixing the world's oceans just at the surface by creating waves. There are three main variables, and we're going to talk about this in lab, but there are three main variables that control the energy behind making waves. Remember, first and foremost, that waves are created by wind, okay? And so the three variables that are going to make waves are the wind velocity, right? How fast the wind is moving. The wind duration, that's how long, right? So here's how fast, how long the wind is blowing, and something called the fetch. The fetch is the distance over which the wind is able to blow. So the distance over which, so over the water, right? The distance over the water which the wind is able to blow. So for example, in the Pacific Ocean, right? If you can want to think about the waves, if this is California, if you want to think about the waves in the Pacific Ocean, if the wind is coming onshore this way, the Pacific Ocean has a huge fetch, right? You have a wide area over which the wind can blow for waves to generate, so you get nice big waves off of California. So these are the three main variables that control the energy that is produced to make surface waves. You might remember from physics, or maybe even math class, that there are a couple of terms that we need to remember when we talk about a wave. So if I just draw a simple sine curve right here, the wavelength, right, is just the distance between the high points of two neighboring waves. The high points are what we call the crest of the wave. So if these are wave crests, the low point between crests is called the trough. So the wavelength, right, the wavelength here is the distance between two crests. And they should be, right, successive crests. The wave height is now the difference between the crest and the trough, right? So this would be the wave height here. That's the wave height. The wave period is the number of crests per time. So for example, if you are watching the end of a dock, you're counting the number of wave crests that come by that end of the dock. Maybe, you know, you're counting how many come by per minute or per hour or per second. That would be the wave period. And if any of you have ever been to the ocean and you go charging into the waves, right, and you kind of try to dive underneath a wave and it kind of picks you right back up and stands you back on your feet. If you've tried to do that, right, where say a wave is about to crash over you and you try to dive in underneath right here, right, and you're angled like this, and all of a sudden the wave keeps rolling over you and you get kind of pulled back up and stood upright like this on the sand, you have experienced something called wave base. The wave base is the depth in the water column to which the wave still affects the water movement. If you are a scuba diver, you may have noticed that once you kind of start to get under the water, maybe about, you know, a couple of feet or so, you stop feeling the swash zone of the waves going over you, right? That's because you have now dropped below wave base. You are now below the depth where the waves crashing over top of you are still affecting the water underneath those waves. So wave base is actually kind of this depth to which the continuously moving waves are still affecting the water beneath them, and wave base can change. In fact, wave base deepens during storms. If we kind of looked at a zoomed in version of what's going on underneath a wave, what you would notice is that if you were kind of sitting out here, right, bobbing in the ocean, here you are, very happy. You're bobbing in the ocean. As waves kind of roll underneath you, what you actually notice is that beneath waves are these weird little orbitals, right? These kind of, you actually, when you sit in the ocean, you don't just go up and straight down. That's actually not correct. What instead happens is that you actually will kind of move and rise like this. You'll kind of move laterally a little bit and then you'll kind of come back up again. So you're actually moving just like these orbitals are. So waves kind of generate these little orbits, and those orbits get smaller and smaller and smaller as they get deeper and deeper and deeper. So as those waves start to move closer and closer to the shoreline, the shoreline is going to actually, the depth of the water is going to shallow. So that what happens is that as those orbitals are coming closer and closer to land, do you notice that the bottom orbitals eventually hit the seafloor? But these top orbitals want to keep moving, right? Even though the bottom ones are essentially stopped dead. So that's what happens when a wave breaks at the shoreline. It's that these orbitals at the bottom are slowing down, but the orbitals at the top want to keep going, and that's what causes the wave to kind of get higher and eventually break. So here, in shallower water at a depth less than about 25 the wavelength, right, 0.25 the wavelength, or less than about half the wavelength, the orbits become elliptical and eventually will start to kind of build up on the beach, and then you'll get the waves breaking. Ooh, look at that. Here is a great example. I always wonder if my little GIFs are going to work, right? The waves in this GIF are moving this way, and you are the red dot. So notice how you don't actually just go straight up and down as the wave moves underneath you. You actually move in a circle. And that's what we're talking about by these wave orbitals being generated as the waves are moving underneath you. Pretty cool stuff, right? Okay. So if these orbitals get smaller and smaller and smaller as they get deeper, what happens under normal conditions, right, is that you'll have wave base somewhere right about here. That means that notice that below this depth, we essentially have the orbitals are way too tiny. They don't affect the water column anymore. So this point right here where the orbitals don't affect the water column anymore, we call that wave base. So the water down here essentially, right, is calm. However, and we would have the depth, right, to the wave base would be about this. During storms, however, the wave base deepens. Okay, so notice now wave base is much, much deeper. Whoops. So now the orbitals actually affect more of the water column, and they can really start to maybe kick up all the sediment that's down here. And that's why waves at the beach during a storm usually tend to look a little bit murky. They're now actually, right, the wave base has deepened. The waves are actually able to not only affect the water column, but they're also affecting the sediment underneath the waves. And it's really kind of stirring up and kicking up a lot of stuff. And that's what makes those waves look kind of like chocolate milk. So the waves are constantly going to be coming into the shoreline. Okay, so the waves are going to be driven by wind, and they're going to constantly be coming on shore this way. But what's cool about it is that the shape of the coastline, notice how this shape of the coastline is actually kind of a horseshoe shaped like this. The motion of the waves is actually going to be affected by the shape of the shoreline. And so if you have kind of a rocky point here versus kind of an embayment back here, you're actually going to change the way that the waves interact with the coastline as they come in. So let's look at this a little bit in terms of how the shape of the coastline is going to affect the shoreline. These kind of embayments like this, and then these rocky points out here, what tends to happen is that as waves come in, waves are going to be focused at these rocky points. So that means that at this rocky point, right, all of this wave energy is kind of constantly pounding against this spit of rock right here. So you get erosion at these rocky points because all the waves are kind of concentrated. Same thing at this rocky point right here, right? Now, alternative to that, all the energy is really focused here, right? So the waves that actually make it into the embayment are much, much slower. So what you get back over here is not erosion, you get deposition. So you get erosion at the rocky points and deposition at the embayment because here the energy is concentrated. You concentrate the energy here, and here it's very gentle and dissipated. So the shape of the shoreline, right, whether you have rocky points and embayments, will kind of influence and target your wave energy to create points of erosion and points of deposition. So along those same lines, we create what's called wave refraction. Wave refraction means that you're actually going to have the waves coming in as like, straight lines. But what can happen is that the wave front, right, the actual wave angle can bend, and we call that wave refraction. Wave refraction can happen due to the shallowing of the sea floor, but it can also be due to, like what we just saw on the previous slide, waves can bend and refract and concentrate their energy at rocky points and dissipate it away from those kind of gentle embayments. But so here, wave refraction means that as the waves are coming close to the shoreline, notice that as the waves are coming close to the shoreline, I'm drawing them so that they're not perfectly parallel to the beach, right? Waves don't actually come in perfectly parallel to the beach. They actually come in at an angle like this. Okay, now if the waves are coming in at an angle, and notice that the water starts to shallow, right, closest to the beach, that means that over here, these parts of the waves are actually going to slow down first because they're starting to feel the shallowness underneath the beach over here, right? So this side of the wave is going to slow down, but this side of the wave is still in deeper water, and so it can move as fast as it wants. And so what will happen is that this part of the wave will slow down, this part will keep moving, and the wave will actually start to bend a little bit, and it will bend in towards the beach. That's the part that we're talking about here of wave refraction. If one part of the wave slows down, the rest of the wave will kind of bend to make up and compensate for the end that is slowing down. So you'll notice here's a great example of how you can see this even from the air. You'll notice that the waves are coming in. So here's the wind, right, coming in, creating the waves. Here's the wave crests. But these wave crests over here are starting to slow down because they are reaching the shallow parts of the beach first. And so these parts of the waves are actually then going to start to bend a little bit more towards the shoreline because they're still feeling deeper water. So here's the wave refraction in this picture here, showing that the right side of these waves is going to bend around and refract because the left side of the wave crests is starting to slow down. And so that wave refraction now is going to do what we were talking about on that first slide there about kind of concentrating. The waves are actually going to kind of be bent towards, they're going to refract towards those kind of rocky points, those rocky headlands. And so you're going to get those erosive things here, right? So we're going to cause increased erosion where you have refraction towards the rocky headlands, and then where you kind of have things bending slowly and more gently towards those sandy beaches, this is where you're going to get increased deposition. And all of this is formed by wave refraction. Now, so we talked about the shape of the shoreline, how we can actually get wave refraction. And now let's talk a little bit too about how we're going to change waves by changing water depth. And we're going to go back to this idea of the orbitals and creating breaking waves. So we kind of alluded to this already. What happens when the water depth becomes less than 1/2 of the wavelength? So if you've got now a wave, right, and it's got its orbitals beneath it like this, whoops, that should have been a little smaller. What happens when it starts to reach, right, a shallower coastline like this? Imagine this is moving inland. What's going to happen is that those bottom orbitals are going to slow down, right? They're trying to move, but now they're going to reach the sea floor. So the wave is going to slow down. The wave length is going to shorten. Now remember, what's the wave length? It's the distance between two crests, right? So I got to put another wave in here and a trough. So the wavelength is going to shorten. Okay, so the waves are going to get closer together. The wave height is going to increase, right? So this actually, the wave height is going to get higher. And what will happen is because the bottom part of the wave wants to slow down and the top part wants to keep going, what eventually will happen is that the wave will break, right? The height ramps up, and then this stuff is still moving while the bottom of the wave has slowed down. That's how you get breaking waves. So here's a great way of describing it, right? Here's your wave coming in when it's still a swell. And notice that now as the bottom parts of the orbitals start to hit the shallow sea floor, the wave is going to kind of ramp up and steepen. The wavelength is going to get closer together, and eventually you'll get breaking waves. So the steeper the coastline, right, the faster the coastline shallows, usually then the taller you get your waves, which is one of the reasons why California has much bigger waves than North Carolina. North Carolina has a very broad, shallow continental shelf that doesn't ramp up very quickly. California, on the other hand, has a very steep continental margin, and so the waves can ramp up and get tall very quickly. If you are like me and you were ever at the ocean, at the shore as a kid, my mom used to always tell me, go into the water, but you have to stay right here. I have to be able to see you, so don't go anywhere other than this, 30 feet in front of me. And 20 minutes later, you see your mom screaming and yelling at you from the beach because she's a mile and a half down the beach, and she's saying, I thought I told you to stay right here, 30 feet in front of me. Well, you can just say to her, Mom, it's not my fault. I didn't do it. It was longshore drift. What am I talking about? When I was a kid and you jumped in the ocean, right? Try as you may to stay in that, between this lifeguard stand and that lifeguard stand, it would never happen. You would almost always end up drifting down the beach. And that is a real phenomenon. It's called longshore drift. And it happens because of this wave action and the refraction of waves as it comes to the coastline. So let me show you this here. Here's the wave crests, right? They're coming in. And what happens, at least in this picture, this is showing you kind of movement along the east coast of North America. The left side of these waves is going to slow down first, right? Because they're going to reach the shallow parts of the coast first. What that means is that as these waves come in to the beach, they're not going to come in perfectly parallel. They're actually going to come in at an angle. So when the waves rush up the beach, they're going to come and rush up the beach at an angle like this. Now, what happens is that once the wave water rushes up the beach, gravity is going to pull it straight down the beach back into the ocean. Then the next wave front is going to push it up at an angle, and then it will have gravity pull it straight back down. Do you notice how I'm drawing my arrows, right? I'm drawing it kind of at like 1 o'clock on a clock, and then back down, and then at 1 o'clock, and then back down. The net movement is, in this picture, always going to be to the right. Sand grains do this, water does this. If you've ever watched a seagull, right, sitting out here, I have no idea how to draw a seagull. Here, beak, feet. Seagulls floating in the ocean will do this. Logs, debris flows, debris rather, buoys or whatever else sitting out there, they will also do this if they're not weighted down. This is longshore drift. It's the movement of sediment or whatever else, and you're moving it parallel to the shoreline because of the wave refraction up on the beach in the surf and swash zones. So the longshore drift is the movement of sediment. The actual net movement of water is what we call the longshore current, right? Current is a word that we use for water. Drift is the word that we use for moving the sediment and the stuff by that water. So this all happens. Longshore drift is a very important, very real problem at the oceans. And part of it has to do with the fact that you can spend a lot of money and you can pump a whole bunch of sand right up on the beaches here. But then over time, all that sand is essentially going to move in the direction of longshore drift. We can see longshore drift if you just kind of stand at a coastline and you look at anything that is kind of built out into the ocean. What I mean by that is, notice that in this picture here on the left, we've built kind of what's like a jetty or a groin. Right here, we've built it out into the ocean. Notice that the beach is way out here in this picture. Okay, there's a lot of sediment built up. but that over here, the beach is way back here. Big problem on passive margin beaches, actually, because what has happened is by building this jetty or groin way out here, what we are doing is we are essentially putting a barrier to catch sediment or sand moving by longshore drift. So now look, if longshore drift is trying to move sand to the left in this picture, right? If it's trying to move it this way, and we put this barrier here, we're going to collect sand here. So you get what's called updrift deposition. We're on the updrift side, right? Because we are up opposite the longshore drift direction. So we get updrift deposition. Great. So our groin is working, right? This guy's beach over here on the right, this guy's beach, he's very happy, right? Because he's got lots of sediment. But what do you notice? Downstream, right? Downdrift, you get erosion. So you actually get erosion on the downdrift side, and this is a big problem. Because now, if you are the homeowner that lives on this side, right, you are very unhappy because your neighbor just stole all of your sediment. Another problem with this, for example, I don't know if you can see in this picture, this is New Jersey, right? This is actually Sandy Hook right here, not Sandy Hook, Connecticut, where we had the school shooting years ago. This is Sandy Hook, New Jersey. And actually, this is New York City, right over here in the distance. This is a big shipping channel right here. This is going up into the Raritan River and the, several of the New York harbors. Longshore drift off Sandy Hook is moving in this direction, which means we're constantly adding sand to the spit here of Sandy Hook. That's a big problem because we're constantly putting sand into this big shipping channel here, and they constantly have to dredge it and get all that sand out of the way. So longshore drift kind of creates some problems for coastal regions, whether it be this kind of, downdrift erosion or this kind of constant buildup on these spits where they have to then continuously dredge shipping channels to keep them open. Here's another great example. Here's Long Island, New Jersey. Long Island, New York. This is another great example. Do you see right here, right? There's a groin built right here. And you'll notice that you can just look at this groin and tell me what's the direction of longshore drift. Notice you've got this beautiful buildup of sediment. And the buildup of sediment should always be on the updrift side, right? So this is the updrift side. You should get downdrift erosion. And if you look really closely, what do you notice? Ooh, there's the erosion side right there. So I could tell you just by looking at this picture that the longshore drift in this picture is moving in this general direction, right? Pretty big problem. And you'll notice too, if you're really good, you can actually see, look at all these groins that these people are trying to put in up here, trying to catch sediment. But then there's kind of this constant problem of, well, if you put in a groin, then I got to do it, then I have to do it, and then I have to do it. And so it's this kind of constant ongoing battle with folks who have coastal properties. Another big problem that happens at coastlines is rip currents. And I'm sure you've heard of these. We do often get warnings about rip currents, especially at the North Carolina beaches. Our wave fronts are coming in, right? And they're coming in to the beach and they're piling up a lot of water. And so as wave fronts are coming into the beach very quickly, they're piling up a lot of water on the beach, but that water has to want to go back out, right? That water has to make it back out into the ocean. But meanwhile, more wave fronts are actually pushing in. So what tends to happen is that you pile up a bunch of water on the coastline out here, and that water tends to funnel back out into the ocean through a very narrow zone. And when it does that, it creates a rip current. So this is where the rip current would actually be formed, right in here. It's this zone here where all this water from the beach is trying to make its way back out into the ocean. Now, you guys remember too, if you ever do get caught in a rip current and it's pulling you back out into the ocean, okay, the one thing you never want to do is you never want to try to swim opposite a rip current. It's fruitless. You will exhaust yourself and you may not be able to get out of the rip current. One of the best things to do is if you're ever stuck in a rip current is to swim to either side, right? Rip current channels, rip current zones are going to be very narrow. So don't panic. The first thing you want to do is just swim to the side, okay? You will eventually get out of the rip current, you'll get into the general wave fronts, and eventually you will be brought right back into the beach. Here's a great example of where they were trying to actually map out on the North Carolina beaches. They were actually showing with a dye tracer where the rip currents were. And so you notice they put the dye here at the beach, right? You can actually see that this is where they put some of the dye. The waves are coming in this way, but this is where the waves are coming back out. So that's actually showing you exactly where the rip currents are. And all they're doing is kind of showing you by dye where is the water being sucked back out into the ocean. And again, notice if these are little beach umbrellas for scale, these are people. It's a very narrow zone. So if you did get stuck in this rip current, all you had to do was move sideways and you would be brought back in. Okay, so we've done stability of the coastline, we looked at coastline sediments, and we've looked at wave energy. If you want to take a break, this would be a good time to take a break, and then when you come back, we'll talk about tides and then long-term changes in sea level. Okay, I'm ready to talk about tides, so let's go ahead and discuss tides that we have at the coastlines and when we sometimes have some kind of spectacularly high and also some pretty decent low tides as well. First of all, what creates ocean tides? Well, we have to kind of imagine that you're looking down at the Earth and you're looking at the North Pole. Okay, so you're literally looking down at the Earth's rotational axis right here, and that we're spinning around that rotational axis this way. Well, around the Earth, we actually have this kind of envelope of water, right? And that the envelope of water reacts to the pull of the Earth's moon, but also a little bit to the Earth's sun. So where the moon is, there is kind of this pull, this gravitational pull, not necessarily on the Earth's solid planet, but on the water envelope around the planet. So where the moon is, we kind of pull on the Earth's envelope of water and we create a bulge. Okay, so here's the bulge on the side closest to the moon. And then there's actually another bulge on the back side because we kind of flatten the Earth's envelope of water so that it kind of pulls this way, right? And we flatten it here. So what that means is that the part of the planet that is facing the moon or that is opposite the moon, they experience high tides. And the places that are actually perpendicular to the moon are experiencing low tides. But remember, this isn't static, right? The Earth is actually rotating underneath this envelope of water. So as the Earth rotates once per day, you're going to have a high tide, a low tide, a second high tide, a low tide, and then go back to the beginning. So every day, every location on the planet gets 4 tides, 2 high and 2 low. So we have daily tides, right? 2 high and 2 low, but they're different heights, right? The time when the first high tide, when the actual location, for example here, is facing the moon, you'll get the first high tide, this will be higher than the second high tide when you're on the opposite side, right, of the moon. So here, if you look at the kind of tidal height, and this is one day, you'll get a high tide, a low tide, a high tide, and a low tide. And one of the high tides will be higher than the other, and that's the one where this is where you were facing the moon. Okay, so the moon, remember, the moon creates the bulge in the world's oceans, and the Earth is just spinning beneath it. That's why in 24 hours we get 2 high and 2 low tides. Okay, now sometimes we get kind of these special conditions where the Earth, the moon, and the sun are all aligned. So you can get a situation where you get something called a spring tide. Now, it doesn't have to happen during the spring season, but a spring tide is where the Earth is feeling the pull from the moon, and either the moon can be between the Earth and the sun, or the moon can be on the backside. Either way, the Earth, the moon, and the sun are all in alignment, right? If they're all parallel to each other, the moon is pulling on the Earth's oceans, but so is the sun, and they're actually pulling all in the same direction. So spring tides mean that your tidal ranges are going to be at their maximum extent. The high tides are really high and the low tides are really low. So you see occasionally spring tides, and you'll see then a big difference between each daily high tide and low tide couplet. Now, sometimes you get the Earth, the sun, and the moon at perpendicular angles. So if this is the Earth, here's the moon, and here's the sun. If the moon is at a perpendicular angle to the Earth being in line with the sun, and it can either be, either situations like this, you can actually now have the sun pulling this way and the moon pulling at a perpendicular angle, and you get a situation called a neap tide. You create minimum tidal ranges here because the sun is pulling in one direction and the moon, depending on where it is pulling at a 90-degree angle from that. So while the sun is pulling to the right, the moon is pulling 90 degrees from that, and so that the moon is actually kind of weakening the sun's pull. So the high tides aren't as high and the low tides aren't as low. So you get what are called minimum tidal ranges during situations called neap tides. Now, there are also some really cool places on the planet where you just get crazy tidal ranges. So in the Bay of Fundy in Nova Scotia, here's what notice this is just an island, right, sitting offshore. This is what low tide looks like. Notice how you have totally exposed beaches, right? I've been out there doing field work and whatever else, and then 6 hours later, notice this is the same island, right? And now everything's covered in water. In Nova Scotia, you get tidal ranges, so twice a day, right? You will see tidal ranges of 20 to 30 meters. Okay, that could be up to almost 100 feet. Here's another good example of what happens in Nova Scotia, right? Here's low tide, same exact image. Here's high tide. Notice the boats are literally just kind of sitting on the sediment surface, right? They're sitting on the bottom. And then when the tide comes in, whoop, the boats are back up floating. This is just a weird phenomenon that happens at the Bay of Fundy. And there is a video clip down here. If you want to watch it, you can see it in like a time-lapse video. Tides increase so quickly in the Bay of Fundy that you actually can videotape it and walk with the tide as it increases. It's really cool. Mostly that has to do with the shape of the Bay of Fundy. The Bay of Fundy has this little tiny opening, this little tiny neck where water can get in and out of. And so what happens is that the tides rise in the world's oceans, and all that water builds up and has to rush into the Bay of Fundy, and that's why the tides rise so quickly. But it's a pretty cool phenomenon. You can check out that video if you have some time. All right, so we're on to our last discussion here. We've already gone through, right, the tectonic stability, the nature of the sediments. We discussed waves and we did tides. Now I want to talk about long-term changes in sea level. And we're kind of segueing into a discussion that we will also have next week, which is about climate change. What are essentially the changes in sea level, and how is that related to things like glaciers or global warming? Sea level has changed dramatically over time, okay? So let me orient you really quickly. The sea level change is shown on the y-axis of this graph, and it's shown in meters. And then at the bottom here, this is time, okay? And this is geologic time, so we're looking at millions of years ago. So present day is here at 0, and back here, this is 542 million years ago at the bottom of the Cambrian period. You'll notice that the blue line is essentially this blue line shown here that says the Exxon sea level curve. This blue line here shows that sea level has dramatically changed throughout geologic history. And what is the major driving factor of sea level? Well, a lot of it has to do with ice ages. When you have warm periods throughout geologic history, we don't have a lot of ice on land. Where is all that ice? It is water, and the water is sitting in the oceans. So during warm periods, sea level is very high. One of the warmest time periods that we actually had in the past was during the Cretaceous, right? During the time of the dinosaurs. And so notice, right, sea levels are very high because it was very warm during this time period here. Now, when you get cold periods, right, when temperatures globally get very cold, what happens is that water that evaporates from the oceans gets into clouds, and those clouds move over land. Those clouds then rain or snow all their precipitation out, and the water gets locked up on land as ice. So we make glaciers, okay? So we make glaciers during really cold periods. What that means is now the water from the ocean is now locked up on land in those glaciers, and sea level goes down. So by looking at this sea level curve, I can say that most likely during this time period here, global conditions, because sea level was low, global conditions were probably very cold, and we had lots of continental glaciers. And that is actually true during the Carboniferous and the Permian. We definitely did have lots of widespread cool temperatures and continental ice. So we know that sea level fluctuates, and that one of the major drivers of sea level change is how much ice we have on land. Now, let me just take a moment to pause here before I talk about this slide. It's very important to remember that the ice that we're talking about has to be on land. If you take, and you can try this experiment, go fill a cup a cup with ice, right? And then fill that cup with ice with water all the way up to the top, and then let it sit and let the ice melt. When that ice melts, will the cup overflow? The answer is no, because the ice that's in the cup is displacing enough water equal to its mass, right? So when the ice melts, the water just essentially takes up the same amount of space that the ice did. So when we talk about sea level rise, we are not talking about sea ice, right? So you're not talking about icebergs or anything like that. We have to be talking about ice on land, because ice on land, when it melts, adds water to the ocean. But when ice in the ocean, sea ice, when it melts, it doesn't create a net change in sea level. Just like if the ice melts in your drink doesn't overflow. Okay, just wanted to make sure I said that. We know that sea level has changed dramatically in the past. And in fact, you might have looked at that previous slide and said, well, how do we know that sea level was higher in the past? We can actually look at coastlines like this, and we can see that, you know, this is where the beach used to be, because we have this feature, right? These little kind of what we call wave cut benches or wave cut terraces. That tells us that at one point the waves were cutting in up here, and then sea level dropped. And then the waves were cutting this little wave cut bench here, and then sea level dropped again. So we can measure the heights of these wave cut benches and figure out what sea level had been doing in the past. Sea level change, sea level rise, movements of coastal sediments create a big problem when humans try to kind of live at the coastline. So I want to talk about how all these different things kind of create a major problem at coastal regions that we have, which is called coastal erosion. Look at this map here, and we even have, right, here's Hawaii also, and here's Alaska. These are showing you places along the US coastlines where you see relatively stable conditions, right? That's the gray. The orange is where you have moderate erosion, and the pink is where you have severe erosion. And what you'll notice is that, right, places that have severe erosion, looks like the Gulf Coast, lots of the East Coast are having problems with severe erosion. The northern coast of Alaska looks like it's having problems, and we're also having moderate erosion along the entire part of the west coast. So pretty much most of the coastline of the US is under at least moderate to severely eroding conditions. Part of this is due to, of course, sea level rise, but also due to wave energy and whatever else. So how do we deal with the concept of go back to the first slide. Remember, we talked about how we have hundreds to even millions of people living right at these coastlines. And how do we deal with the problems of coastal erosion and coastal flooding if there's so much population that wants to live near these areas? Here is a great example of a bunch of beach houses. These are actually on the Outer Banks, and I know that because right here's the Intercoastal Waterway behind it. Here's the open ocean on this side. And so before a hurricane, right, you see all these gorgeous, huge houses. They've got all of their beach access all set up. But then remember, too, that, you know, the best planning still can't really account for the damage that can happen during a hurricane. And unfortunately, this is the same image. And you can actually see here's that little red house that we were just looking at on the previous slide. This is the after, right, after a hurricane. These houses were all built on stilts and whatever else. In fact, you can see, look, they're built on stilts, right, so that floodwater goes right underneath it. But I'll tell you, hurricane damage kind of you really can't plan for it. These houses were absolutely demolished. And so living at the coastlines due to coastal erosion, hurricanes, whatever else, is certainly challenging. So what determines whether a beach is eroding or whether that beach is stable? Essentially, what we want to talk about is something called the sand budget. What the heck is the sand budget? Well, super easy, right? Any sort of budget is, right, input, that's supposed to be an N, input versus output. Any budget is going to be input versus output. So what's bringing sand to the coastline versus what's removing sand, or what's the output of sand at that same coastline. So the sand budget is essentially the rate at which sand is input, supplied to the beach versus the rate at which it's being removed, right? That's the output. So what are the inputs and the outputs of sand to the beach? Well, of course, you just saw one major output, right? That can be things like hurricanes, and could also be things like longshore drift, right? Longshore drift can actually help move stuff off the coastline. So what are the ways that we actually then get sand to the beach? First, I want to talk about what are natural ways that we can get sand to the beach. The inputs to the beach are going to be things like sediment eroding from cliffs, right? So literally, you're going to have cliffs eroding and adding sediment to the beach that way. Sediments eroded from updrift beaches and being brought down by longshore drift. Or the biggest input of sand to beaches is sediment brought in by rivers. Okay, so here's a big input right here of the river bringing in sand. Those are ways that we can get sand naturally brought down to our beaches. What are the big outputs? Well, sometimes the wind, believe it or not, wind can actually be blowing onshore, and the wind can actually pull sand off the beach and move it inland. You also can then have sediment transported away from your beach by longshore drift. Or you can actually have it kind of drop down the continental slope by tides or currents, transporting it down into the abyssal plain. Once it gets off the continental shelf, it's actually really difficult to bring it back up. So we consider this to be an output because once that sediment gets into the continental slope and the rise, it's really hard to kind of bring it back into the sand budget. So remember, the sand budget is just how fast are you inputting versus how fast are you outputting sand to your coastline. I'm beating a dead horse here, but this is just kind of another graphic that shows the same idea, right? That here's your inputs, right? Places that you're actually bringing in sediment or reworking it, right, along longshore drift. And then here's your places where you're losing it. There's wind, there's offshore, or you could be moving it by longshore drift. Outer Banks, North Carolina. This is the town of Rodanthe. Okay, this is the town of Rodanthe. If you watch the movie, you don't have to admit it, it's okay. It's a Richard Gere movie. If you watched Nights in Rodanthe, This is the Serendipity house right here. This was the one that was actually featured in the movie. Notice, right? It used to be, this coastline used to be way out here, and there was actually quite a bit of beach between all these houses. After a couple of big hurricanes in 2008, notice how the beach is now back here. These houses are literally now sitting in the surf zone. This is all floodwater back here right after the hurricanes in 2008. So big problems associated with the Outer Banks and hurricane storms and coastal erosion. This is another view now. It's the same exact, here's the Serendipity house in Rodanthe. I'm just now looking in the opposite direction. And notice that now they're trying to move all the sand and stuff like that to try to kind of get things back to normal. This is I think it's Route 16, I think, down. This is the only inlet and outlet for cars and people onto the Outer Banks. And you can tell in many places, right, it was flooded and compromised. This was such a popular house. So many people know this Serendipity house in Rodanthe that after the hurricanes in 2018, they actually decided to move this house to try to save it from coastal erosion. They literally put the house on a trailer and the whole thing, they literally just moved the house on a trailer. The problem is they only moved it down the street by about, a couple hundred feet. So it's still, they spent a lot of money to move this house, and unfortunately it's still right there in the danger zone, but at least they were able to save it, and it wasn't demolished by subsequent hurricanes. But notice that in 2010, they did finally move it just down the street, and it still is in Rodanthe. So coastal erosion, major problem. How do we deal with it? Okay, what are the ways that we can actually alter the sand budget, not by natural terms, but by maybe, human intervention? We can do two things, right? We can actually build structures, so we can have a structural approach, or we can not build structures, but we can actually kind of do things to work with the kind of natural processes of sand moving around on our coastlines. Now, let's start by looking at the structural approaches, and I'm going to pick on New Jersey for a little bit, and I'm allowed to do that mainly because I'm from there. So Jay, work with me here, bud. But yeah, we do a lot of things in New Jersey that a lot of folks in North Carolina haven't actually seen, because North Carolina beaches are very broad and generally speaking are not eroding as bad as the ones in New Jersey. Now, New Jersey beaches are eroding significantly. So we have built a lot of structures, right? We've literally built these things called groins, jetties, seawalls, and breakwaters. And we're going to look at these individually in lab, excuse me. But these structures are built out into longshore drift, and they're built to try to catch the sand that is trying to move along the shorelines. Groins work really well, so do jetties. However, they have to, you have a little bit of a problem, because remember we talked about groins and jetties. They do help catch sand from longshore drift, but they create downdrift erosion. So groins are these structures built perpendicular to the shoreline. Notice, right, person for scale, notice the beach is out here on this side, the beach is out here on this side. So if we get updrift deposition and downdrift erosion, which is the way that longshore drift is moving in this picture. If you said this way, you're absolutely right. So here we've built a groin perpendicular to the shoreline to trap sediment, and we're trying to mitigate beach erosion. But remember, we're only creating deposition on the one side. You actually exacerbate erosion on the other side. Here's another good example of a groin, right? We know longshore current is moving in this direction, because notice we've got a huge buildup of sediment over here, but we have erosion on this side. And so once again, we've built a groin, we've trapped deposition of the sediment on the updrift side, and we've created erosion on the downdrift side. So we definitely know that now longshore drift in this region is moving this way. So groins are functional. They actually are, they do what they're supposed to do. However, remember that even though they create a buildup of sediment on one side, right, they'll get the deposition on one side, usually it exacerbates erosion on the other side. So when you build one groin, usually you then have to build, right, another one and another one and another one. So we'll look at in lab the coastline of Long Island, and you'll see literally groin, 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 because every time you put one in, you make erosion worse on the downdrift side. And so the next homeowner usually puts another one in. Jetties are something that we build perpendicular to the shoreline also, but jetties are built to keep inlets open. Okay, an inlet is a connection between the ocean on one side and either a river or a sound or some other body of water on the landward side. Because, right, sediment tends to kind of want to fill up these inlets in these oceans, we build these jetties to keep those inlets open. Now, you can actually look at this picture of this jetty here too, and since they've drawn it correctly, I'm going to erase all my stuff here. You can tell me what's the direction of longshore drift here. Notice, see how they've drawn this? You're getting deposition here, erosion here, longshore drift moving this way. The last thing that we're going to talk about too are, and we'll talk about this in lab, are breakwaters. You can actually just put a big breakwater, a big concrete structure out in the ocean, but it's parallel to the shoreline. And because of wave refraction, right, you're going to bend all your waves. And so the waves are going to beat up on the breakwater, and it's going to make the stuff behind it pretty calm. What that means is that actually now you kind of alter the sediment here. You'll create erosion on either side of the breakwater, and you'll get deposition behind it. So you can alter the shape of the coastline that way just by putting in a breakwater. Ocean City, Maryland is actually seeing a big problem with longshore drift and putting in jetties. If this is in the map view over here, here's Ocean City right here. And so they've built a jetty here, and they built another one right in here. Longshore drift is in this region moving to the south. So you'll notice that that's great. They made a nice big wide beach in Ocean City. But here's the problem. Remember, you get updrift deposition, but what do you get on the downdrift side? You get erosion, right? This is pretty crazy. This black outline here used to be where this island here used to be. Because we've actually starved so much sediment by downdrift erosion because of these inlet jetties right here, this island has actually eroded and migrated landward to where now it's sitting here. This is pretty crazy. You can actually even see this up here in this diagram, right? Here's the jetty. This is Ocean City right here. The island used to continue here, but now it's all actually been moved inland because of the erosion, partially based on the jetties, but also just because of storm activity. But essentially by trapping all the sand up here in Ocean City, we've kind of stolen it from the island down below, and the island has actually started to erode and move inland. That's what happens when we use structural approaches to coastal sand mediation. Now, you can also use something called beach nourishment. Now, this is a non-structural approach, right? We're not going to build anything, but what we're going to do instead is we're going to artificially add sand to the beach. So we're going to essentially increase, right, the input. Knowing that, sand is going to move and be removed from the beaches, we know that there's an output, but we can actually now truck in or pump sand artificially onto the beaches so that we can actually replenish what's being removed by the output. In New Jersey, or in several places along the East Coast, we call this dredging. What we'll actually do is we will have ships parked just off the coast, and those ships will have huge tubes that will be sucking sand up off the seafloor just outside the breaker zone, and they're going to pump that sand up onto the beaches to make the beaches wider. If you look at this here, right, this is a kind of a time-lapse GIF here, the distribution and relative amount of money spent on beach nourishment over the last 25 years in the US. The hotter the colors, right, the more money and the more focused the efforts have been on beach nourishment. I tell you, New Jersey spends a lot of money trying to nourish its beaches. One of the reasons is because, of course, right, it is a huge tourist amount of tourist income. Notice how as we get further and further, I think this goes up to 2011 or 2012, right? You can see that the East Coast is really doing a lot to try to spend as much money as they can to keep their beaches stable, and also to keep them relatively wide and relatively, up to 2014, and bringing in a lot of that tourist money. Here's what dredging looks like. Okay, so here's the boat is literally sitting just off the beach, right? There are pumps back here, and they're sucking in sand from just offshore. And then these kind of huge jets are blowing that sand and water onto the edge of the beach to kind of widen the beach. This is what it looks like, right? Here's Cape May, New Jersey. Here's the before, right? Here's your before picture. And here's after. Look at these nice big broad beaches, right? Looks good. Here's the hotel. Here's the same hotel right there. Notice the nice big beach. So dredging does work. However, it is extremely expensive, okay? Beach nourishment, dredging, whatever you want to call it, is a good thing, right? It's not building a structure, so it doesn't cause any sort of downdrift erosion. However, it's extraordinarily expensive. And because longshore drift is going to keep reworking and removing all of that sediment, it has to be repeated periodically. I mean, it could be on the order of every couple of years. And because it's so expensive, if you have to keep redoing it every year, guess who's actually paying for all that stuff? The local and the federal taxpayers. Here's an example of this, right? We do a lot, this is New Jersey, right? We do a ton of dredging in the southern parts of New Jersey, but longshore drift moves all that sediment to the north where it's being deposited at Sandy Hook and closing that shipping channel with New York, right? This was from a couple of years ago, these statistics, but let me just show you this. New Jersey beach replenishment, right, or beach nourishment, it costs $60 million per mile. $60 million per mile, okay? The Army Corps of Engineers wanted to make 100-foot wide beaches along 127 miles. Okay, $60 million per mile times 127 miles. Cool. Experts predicted that this series of projects would cost more than $9 billion over 50 years. And guys, check this out. 65% of which would be funded by federal taxpayers, not New Jersey taxpayers. You guys, federal taxpayers. Here's the other kicker. Costs of periodic re-nourishment might even be higher because of high erosion rates, which means that they would have to re-pump or re-dredge every 6 years. I mean, that's pretty crazy, right? That just, $60 million per mile, $9 billion over 50 years, but that they would probably have to keep redoing it once it was done every 6 years at the same cost. So this is pretty crazy stuff. This is very high dollar stuff because you can imagine, I don't even know what the state income is from tourism at the Jersey Shore, but I can only imagine. So it's very important for coastal states like New Jersey to have their beaches, up and running in the summer times. But it is, of course, at a very high cost, not only to the local taxpayer, but also to the federal. But again, one of the things that we can do with beach nourishment is that we're not building out any sort of structures or jetties or anything like that. You're not upsetting any sort of coastal environmental ecosystems, but you certainly are costing taxpayers a ton of money. And also too, that sand will eventually keep moving and you will have to replenish.